Welcome everyone and thank you for joining today's webinar. My name is Abdurrahim Balaysawi and I work as a lead application engineer at CS, the MathWorks authorized reseller in the Middle East. So as Victoria mentioned, in the previous webinar sessions, we introduced the mission engineering approach. We discussed how mission objectives drive the systems and system of systems development. Today we will build on that foundation by focusing on how model-based design helps accelerate the development of mission platforms. Start with this mission scenario. So instead of focusing on the mission itself, let's look at the engineering building blocks that enable it. Here we see multiple platforms like air, sea, ground, space, and supporting infrastructure. All are working together for a specific objective, which is the success of the mission. Each platform has its own design challenges, but they also operate as part of a larger system or a system of systems or even a mission. Today's focus is on how model-based design helps accelerate the development of these platforms by connecting requirements, architecture, design, verification from the beginning of the project development. With that context in mind, let's look at today's agenda and see how we cover each of these aspects throughout this session. We will start by looking at the key challenges in building modern mission platforms. Then we will introduce the model-based design approach and show how it supports the development life cycle from requirements through testing and validation. We'll also touch on the role of AI in modern platform design and acceleration before concluding with a live demonstration where we will apply the model-based design approach to the development of a quadcopter system. To understand the value of model-based design, I would like to start with looking at the challenges or the engineering challenges that teams are facing with the development of mission platforms. After looking at the mission scenario in the beginning, the question becomes, what makes development these platforms difficult in practice? Whether you are talking about aerial, maritime, ground, or space, or even sensing platforms like radar and communication systems, many teams face similar challenges. The very first challenge that is very common is the long development cycles, heavy dependence on physical prototypes, late design changes, slow iterations over the scenarios and conditions, integration issues that are usually found late, and of course, in a disconnected engineering approach, there will be lack of traceability across requirements, architecture, design, and testing. These challenges are exactly where model-based design can help by enabling earlier simulation, faster iteration, better integration, and of course, stronger team collaboration for different life cycle or for different steps of the project development. We have to note here that these challenges not only impact the cost, but also the performance, delay deliverables, and impact the mission success. We would like now to run a survey so that we understand what kind of challenge we are also trying to overcome, and so that we can build on that for the rest of the presentation. So there will be a survey in the chat. I want you to just like share with us what kind of challenges are and your team are trying to overcome. I will also I mean both, because I'm also facing some challenges because we build projects ourselves as well. We build demos, and so I'll also vote for some. So let's wait for like 1 minute for everybody to pick the challenges that are facing in their day-to-day or daily work, trying to overcome challenges associated with mission platform development. All right. I think we can now focus on few of these challenges that are mentioned there in the response. So seems like we have three challenges that are being like being faced by most of you, and we will be talking more about that so that we understand better how model-based design can help overcome them. Speaking about these common challenges, and one that I hear frequently from our customers is the reliance on physical prototypes. While physical prototypes are important in the process of building systems and missions, they are expensive and time-consuming to build. And as a result, teams often have limited time to evaluate design alternatives and iterate quickly over different scenarios and conditions. By shifting the development to the left, which is modeling in this case, engineers can explore a much larger design space, evaluating different other alternative solutions earlier, and continuously improve the design before committing to the physical prototyping. Another challenge that engineering teams are facing is keeping development artifacts connected as the project progresses. A requirement influences the system architecture, which drive the design, the implementation, and the system integration. And as you already know, and everybody is like aware of this, so these phases depend on each other. Every stage at least depends on the previous one. In many organizations, this transition rely on handoffs and disconnected documents. As a result, changes become difficult to manage. So traceability is lost, and errors are introduced in the development process because of the manual steps that are included or involved in different phases. So these challenges, or this challenge which is related to requirements and artifacts, introduce errors and slow down the development process. This is exactly, again, a type of challenge that model-based design can help overcoming. In this process, errors are often also discovered late in the process. And as you make progress, it becomes more costly to fix issues and becomes more time consuming. And as a consequence, cost runs over the budget and the project encounters delays. These challenges, just want to say one more word about these challenges, can be overcome using model-based design, which starts with the requirement all the way to system integration and testing. So the solution for us to explore today is the model-based design approach with MATLAB and Simulink. And I would like to give you an introduction to model-based design before we apply it with MATLAB and Simulink to a use case, which is building a quadcopter system that's going to be our demo, just to remind you that we will have a live demo at the end of the session. So we describe model-based design as the systematic use of models throughout this development process. And there are two major components, modeling and automation. modeling with simulation and analysis to try out new ideas and give you fast, repeatable testing. So we have this question, why model-based design, that we would like to answer by the end of this section, which is model-based design. So modeling and simulation helps cost and speed up design iteration. And I believe that's quite clear to everybody that modeling is not as costly as physical prototyping. So the modeling in this case, we mean by modeling the simulation and analysis. That's the purpose. So we model a system so that we can simulate and iterate over different conditions through what we call the analysis of the system. Also, modeling enables iterations. So we can iterate over different scenarios, conditions, parameters, and so on and so forth. With that, we can do what we call rapid prototyping and testing with less time, or within less time and with less cost. With model-based design, multi-domain models serve as the source of your design throughout all the phases of the development, so that you can eliminate the barriers. So remember the barriers that we saw before. With the model-based design, you can eliminate this, allowing you to capture requirements and link them to artifacts so that you can do the traceability throughout the development process. And remember that the model-based design, the center of it is all about a model or models. Okay. Another answer to our question why model-based design could be automating steps in the design process. For example, coding is usually manual, and verification is disconnected. So people like usually, or engineers, they usually test at the end of the process while they do system integration. With model-based design, you can capture requirements, specify system behavior and architecture, perform simulation, provide a foundation for automation. And with model-based design, you can also automatically generate code from your model for the implementation and for verification as well. So let's look at the verification here. So there are different ways to do the verification. So as you get your requirements in the MATLAB and Simulink environment, you can perform what we call requirement-based testing at the requirement level. We are here not talking about the architecture or the design or the implementation or even the system integration phase. You can do some analysis and verify your requirements early. Then as you progress with building the behavior of the design or of your system, you can perform the early design verification. Some people, they like to call it model in the loop. So you can perform this type of verification. And virtual integration and testing, this is based on code generation. So you first generate a code, and then you can run it on your hardware, the target hardware that you would like to use for your final projects, or maybe just like a kind of hardware that's will help you with verifying your system design. And we have 3 different ways to do that: software in the loop, processor in the loop, and hardware in the loop. The last phase or the last verification step could be the physical system testing. So you deploy your code to your target hardware, and then you integrate that processor or that FPGA into the bigger system. And with that, you can start doing physical testing on your system. With that, you eliminate any errors, and you can also like save time, because this automatic code generation and automated testing will help you with cutting not only the cost but the development time as well. And the purpose of this is to focus on creating innovative platforms design. And that includes not only the design of the plans, but also the algorithms. Usually people are more focusing on improving these algorithms. And so that's one way to, focus on the algorithms and the design of your platform throughout the model-based design approach. Summary: modeling and simulation enables short and quick iteration cycles, save time and costs, and ensure the delivery of products with minimal defects and, of course, high quality deliverables. At this point, we can now answer the question, why model-based design? And I would say the answer is now very clear, is to accelerate mission-critical platform development through connected digital models, early simulation, continuous testing and validation, and of course, bringing teams together to work on the projects using such approach. So maybe now you have a question, should they apply the model-based design as it is, or it's fine, I would say to go with piece of it instead of going with the entire workflow? So the answer for that, model-based design is not all or nothing. Model-based, and we have what we call model-based design adoption grid for that. So we help our customer in the region to understand where are they now and where they want to move, okay? So usually most people, they start with modeling their design algorithms when they get started. I mean, then they move, or some of them, they move to the verification, to this simulation verification of their systems. And many of them are generating code from the model so that they can perform rapid prototyping and embedded code generation. Grid like matures enough, you can do both of these steps. I mean, you can do modeling and simulation, or you can go to the other side from the left to the right and you perform code generation. And with that, you can start performing hardware in the loop simulation, perform real-time testing so that you understand how system can perform when running on a specific target. You can also perform software in the loop and processor in the loop as another verification layer before you move to the certification of your products. What we would like to do now, we would like to run another survey so that we understand where are you now at this adoption grid of model-based design. So I would like to know where are you now, because I want to focus more on where you want to go. Okay, so that's one reason. And the other reason is that we want you to tell us what is exactly the current model-based design piece that you are doing. So there is an option for not using, you are not even using model-based design. If that's where you are now, so please specify that instead. Perfect. We have already 16 responses, and seems like you are already doing model-based design. Some are doing algorithm development, others are generating code, so on and so forth. That's great, and it's good to know that you are already doing some model-based design parts. Okay. Let's now understand more how you can apply the entire process of model-based design using MATLAB and Simulink. So broadly speaking, as I stated before, model-based design can be described as the systematic use of models throughout the development process. And I want you to remember this, flow chart. So we start with the requirement, then functionality and architecture, design, implementation, and finally system integration and test. This is not a one direction or one directional approach, but it's an iterative approach. Remember that model-based design enables this kind of, let's say, quick iteration over different phases. So you can always go back to requirements and then move to the subsequent phase. So at a high level, models are used to develop the system architecture consisting of behavioral models and functional specification that are usually associated with specific design components. Those components are and systems can represent either the physical system, which can be physics-based or using some AI and data-driven techniques, algorithms that can also be models or external code, or can be also an algorithms based on AI. And of course, if you are building a platform, you want to model the environment where this platform going to operate. So the design comes with the architecture usually, and the system architecture describe the behavior model or can be a functional architecture based on the requirements. And MATLAB tools can help heavily with these two phases, and it has a strong simulation rule. In order for modeling and simulation to be effective, you need to be able to combine components and systems from multiple domains together. So these systems can be continuous time models, can be discrete time models, can be physical models, and so on and so forth. MATLAB and Simulink can help you with modeling these components and bring them together to form or to build the system level simulation. For example, by modeling and simulating components that run either continuously, discretely, or even event-based systems. You can also combine these components to create complex systems such as analog mixed signal systems, communication on radar systems, and you can also bring system of systems to your model so that you perform a better and accurate simulation, which can then be further integrated to include, some intelligence into your model that is based on AI, machine learning and deep learning in this case, and even we can use some, in this example, we're using a reinforcement learning as an agent, okay? And so this is another way to use AI for platform modeling. And commonly we use them for system identification if we don't know, the equations of that specific component, which makes our system. So we can use AI or what we call data-driven techniques to build a component that will be then integrated into the system level simulation. And of course, you can create and integrate perception in autonomous systems. This is mainly related to the algorithmic part of the design. All of this can be done within MATLAB and Simulink. So when we say MATLAB and Simulink, we don't mean two different platforms. It's a unified environment, and these two tools, they work together to help you with building such system of systems or even mission simulations. These tools and languages can be integrated with MATLAB, Simulink in a number of different ways. And the reason why we want to integrate sometimes with external tools or third-party software and hardware is to get whatever we have created before. So say that you have a C++ code that you created before, a legacy code that you want to get into your Simulink environment. So that's something called code integration. You bring it to MATLAB and Simulink, you integrate it into your simulation, and you perform simulation, and later on you can even generate the code. So there are different ways to integrate Simulink and other hardware or other third-party software and hardware. Specifically here we are talking about software, but we integrate also with different hardware seamlessly. So these ways can be co-simulation, data exchange, co-generation, and so on and so forth. Going back to our view of the system development lifecycle, this connection and integration of different types of models from an ecosystem of tools and languages that describe both the system functionality and architecture and the subsystem design. From the first thread of the digital thread, where you can trace development of your system from one phase to other. So again, the digital thread or the model is at the center of this process or this approach, which is model-based design. This digital thread can be further extended to capture system requirements by importing or even building, authoring your requirements within MATLAB and Simulink. So you have at the beginning some line of business requirements, a stakeholder coming to you with some requirements and needs. So with the MathWorks tools for requirements, you can, import those requirements from an external tool, or you can use requirement toolbox to build your requirements within the MATLAB and Simulink environment. And in that case, it will be much easier for you to link and perform different testing based on those requirements. Now let's include the subsystem implementation or the code generation part, where code will that will be deployed onto the system in operation is created. So now we are moving from the design to the implementation. We are trying to target some hardware, okay? And specifically, this code can include links that point back to both your system requirements and other models. So you never lose the traceability as you go from requirements to code. I have just one more word. So this generated code can be traced back to the design component, to the architecture, and of course can be traced back to the requirements. Okay. So this is actually accomplished through the use of automatic code generation, and the generated code is usually always like reliable and high performance, and it gives you also the flexibility to choose your target or the hardware that you would like to target. Core platform or MATLAB and Simulink and Stateflow all support this automatic code generation to a number of different targets, whether it's a CPU, GPU, a PLC device, or an FPGA. You can also target specific microcontrollers from NXP, Texas Instruments, and others. On the left side, we have a different way of deployment, and this time to enterprise systems or to desktop. You can deploy your MATLAB and Simulink simulation on big data platforms such as Cloudera and so on and so forth. You can generate cloud frameworks and files in Docker, Kafka, and so on and so forth. Other way is to generate executables that you can run on edge platforms like Windows and others. And then, as I said, you can always trace your code back to the previous phases, the design, the architecture, and the requirements. So you generate a code, and you would like to now, or you would like to understand it, verify it. So one way is to trace it back to the design, then to the requirements. So in that case, you might want to do some requirement changes, and it will be much easier with this model-based design approach to trace back to those requirements and see the changes reflected in the subsequent phases. the testing or the VNV and testing is a very important aspect, and it's very well supported by MathWorks tools. And so there are other tools that can do testing, verification, and validation. But the good thing about this environment is that you can do these things automatically, or what we call automated testing, verification, and validation. So you can, as I said before in one of the slides, that you can perform testing, verification, and validation in different ways, starting with requirements validation, early design verification, virtual integration testing through what we call seal, peel, and hardware in the loop. And eventually you would like to test with your physical system, and that's called physical system testing. Now, we would like to understand how AI can help with building a better platform and accelerating the development. Let me bring back this model-based design view, this chart, this very nice chart, and speak about the integration of AI in model-based design. So AI can solve tasks that are difficult to solve with conventional algorithms or traditional algorithms. So for example, you can use AI to model specific components. This is something I stated before. Or you can use AI as an alternative to some algorithms. A use case or one example that I see a lot from our customers, they are trying to, for example, use AI as a sensor fusion algorithm. So instead of using a Kalman filter, they use LSTM and so on and so forth. And I want you to remember that these models, these AI models, will be part of the model-based design, and they can be also tested, verified, and validated as a piece of the model. Let's now look how we can integrate AI into the model-based design. First of all, development AI models require a lot of high-quality training data. So with simulation models, you can generate sensitive data to components, to add some fidelity to your real-world data or to improve your real-world data. AI models become more accurate when you train them with datasets that cover a range of operating conditions and scenarios, including specific cases and scenarios that are very difficult to cover with real-world data. So with that sensitive data, we can refine our model, improve it, and then verify the accuracy of the training. And this is like a loop, okay? So you can keep iterating over your training phase of your AI model until you get an accurate AI model. These models, you don't need to build them from scratch. If you have something that you have built already, you can bring it to MATLAB and Simulink environment. So say you have a pre-trained model. So with the integration aspects in mind, we can bring these pre-trained models to the MATLAB and Simulink environment and integrate them into the system-level simulation. Same applies for common frameworks used by AI engineers, or I would say machine learning, deep learning specialists. So they use PyTorch and TensorFlow. So with the integration support packages provided by MathWorks, you can import from these frameworks to MATLAB and Simulink. Or the other way, which is training an advanced model from scratch with MATLAB and Simulink, and we have some very powerful capabilities included under deep learning toolbox and statistical machine learning toolbox that help you with building AI models and seamlessly integrating them into your training loop. There are two main ways of integrating AI. So I mentioned that we can use them for the platform design, or we can use them as part of the algorithmic aspects. So with that in mind, we would like to understand further how they can be integrated. So first, AI can be applied to component modeling. In such case, two use cases are very common: system identification and reduced order modeling. AI can also be applied to algorithm development, so you can add advanced perception and sensing capabilities to your algorithms, or you can also use that as a controller or as an algorithm for planning. So with that, you enhance traditional techniques with the integration of AI capabilities into your system design and into the algorithm development. This is a good example that shows how to use AI with model-based design within Simulink. So AI can be applied to solve the perception problem, can be used to create virtual sensors like sensor fusion. I can play a crucial role in modeling system dynamics. And of course, we can build AI-based controllers. So instead of using a basic, or let's say a controller that is not very accurate, so we can train some deep learning model or even just machine learning model, and we replace our controller with that AI-powered controller. Of course, you can use AI as an alternative to decision logic. And this is the simulation of that example. This is the visualization of the scenario. You can look at this as a mission where we are trying to detect and classify different, target using, using different data from different sensors, from radar, camera, and so on and so forth. And all that is based on AI capabilities. And of course, the story doesn't end here. So you would like to take your AI models to production. And the same thing we said about automatic code generation for, classical algorithms can be said about deploying deep learning and machine learning algorithms. You can generate code for CPU. With that, you need to generate a C, C++, or a GPU that's CUDA code, or microcontroller, it's a C usually, or C++. And you can also target an FPGA by generating HDL code. There is one step here that you need to keep in mind, which is model compression, which is well supported by MATLAB and Simulink functionalities. So you don't want to just take your model as it is and deploy it on your hardware. You would like to optimize it and make sure that it's going to run in real time. And that step or that phase is called model compression. And the way you can do that is through the structural techniques. There are many techniques out there to compress the model, or just by changing the data type. In that case, you are reducing the memory usage and so on and so forth. And with that, you are compressing your model. So the next step for you after you compress your model is to generate code and deploy it to your preferred hardware. So now we have been speaking about how to use AI as part of the platform and the algorithmic aspects. We would like now to use AI to assist us with accelerating the development of our platforms. I want to start with just a quick overview how it started with generative AI. So usually, or in the very beginning, we started with traditional chat. We ask AI agent some question, it gives us an answer, and then we do copy paste. And then after some time, we saw the generative AI and tools evolving to writing code, running it, and debugging it. And currently, we are not only talking about that, but we are talking about agentic AI, trying to do the entire process, or the entire development process, from writing code to running it, to fixing it, to testing it, and so on and so forth. If you want to know how AI agents work, so they perceive, then they do some thinking, reasoning, and so on and so forth. And the next step for them is to act, and then there is another step after that, which is learning from the output of their answers. At MathWorks, or with MATLAB and Simulink, the focus is not only about integrating the generative AI, but to, get something which is verifiable or verified. So combining MATLAB and Simulink with generative AI has two types of workflow: technical computing if you are using MATLAB, or model-based design, that's more Simulink. As I said, the purpose or the end goal is to turn some of the probabilistic output into something verifiable that you can trust and deploy on your hardware, or you take to production. And with this combination of MATLAB and Simulink and generative AI, this is what you exactly get. And we will be talking more about that in the next slides. So there are different workflows for you to use generative AI with MATLAB and Simulink. First, we will talk about copilots. Or first, we would like to talk about integrating external generative agents to be used with MATLAB and Simulink. The way to do that is via what we call MCP or VS Code. So if you are using VS Code as an editor, you can integrate generative AI with MATLAB and Simulink through it. The other way is to build your AI agents in MATLAB and Simulink by calling LLMs from the MATLAB code. And MATLAB and Simulink have their copilots, which are optimized for MATLAB and Simulink. These MATLAB and Simulink copilots were trained, optimized using MathWorks documentation, which is, as you know, it's very rich, very has so many data, and that data was used to train, optimize these models that are helping engineers worldwide accelerate their development process with MATLAB and Simulink. Speaking now about the integration of agentic workflows with MATLAB and Simulink, as I said before, it's through what we call the MCP. These are the tools on the right side. These are the tools, and on the right side we have some AI charts and agents applications like VS Code and the Codex and so on and so forth. And we would like to connect them. So as I said before, it's through what we call MCP. So on the application side, we have an MCP client, and on the I would say on the other side we have the MCP server. And the same way we integrate MATLAB and Simulink with this AI chart and agents applications. So the same way through what we call the MCP. So you can also integrate, or you can use your own local agents if you have built any. So instead of using the ones that are hosted in the cloud, you can also integrate with the ones that you have in-house, you're created in-house. And the same way we said about the ones that are provided by or on the cloud can be said about local models. So say that you have optimized a GPT OSS model and you would like to integrate it, is also through what we call the MCP. So in link with model-based design, I would like to speak about one way to integrate AI or generative AI with Simulink environments. And the tool for that is called Simulink Agentic Toolkit, which allows you to connect agents to Simulink, giving them the ability and the knowledge to work with Simulink models effectively. The way we connect it is built on the top of MCP. So the MCP tools for reading, editing, and querying, testing, and checking Simulink models. And the AI or the agent skills encoding are encoding, in this case, the model-based design best practices. So this is the toolkits, and as you can see here, we have something called Simulink skills, and that file or that skill file has the best practices of using model-based design. And the purpose, remember that we would like to get something verified at the end. So we would like to get something that was designed with keeping in mind the best practices of using Simulink with model-based design. So the option or the solution is provided within the Simulink agentic toolkit, and it's enabled by what we call Simulink skills. You can install this and try it at your end. It's free and it's provided by MATLAB. It's actually on the GitHub of MATLAB. So please try it, install it, and you can reach out to us if you would like to have any specific session for integrating AI or agentic AI with Simulink. This is one use case. We will ask an agent, which is in this case Codex, OpenAI Codex, to troubleshoot, fix, and verify a stability control system. So first, we will ask it to investigate the design and find the issue. Okay. So the thing that we should all be aware of is the quality of the prompt that we send to the AI agent. So you have to write a good prompt, and then the agent will do the rest of the work for you. So it's now looking for the issue. And then we can open the subsystem where the issue is located. Okay. Next, we can ask it to fix the issue. Fix it for me. So it's going to fix it for us by implementing maybe a different block, or maybe just playing with parameters. So it's up to the AI agent to fix the issue in this case. So it's now fixing it, editing it, reading it, and testing it. Remember that the agentic AI workflow doesn't only like fix issues, but test the model after fixing those issues. Okay. This is one use case. There are many other use cases that we would like to run a survey about. So we're gonna send another survey in the chat. We would like to understand how you would like to use agentic AI with MATLAB and Simulink. Let me also go to the charts. Okay, I already see many answers. That's great. Thank you for answering the survey. So next, we would like to move to the demonstration. So the demo, or the live demo, is about designing and testing a quadcopter system. Not only the platform, but we will try to map this project to the model-based design approach, from requirements all the way to the system integration, virtual testing, and virtual integration and testing. So that's actually the live demo. Let me just like walk you through the workflow again, and I'm bringing back the development process flow chart. We start with requirements and functionality and architecture, design and simulation, implementation, and then system integration and tests. That's exactly what we have been talking about since, I believe, the start of this session. And we would like to apply it to this use case, which is a quadcopter system design and testing. I will jump now to MATLAB. Okay. And this is my project. So saying that we would like to validate quadcopter systems and system architecture with simulation. We're gonna start with defining requirements, build the architecture, then iterate over that architecture so that we include the security requirements. That's something we'll not include in the beginning. We will just start with the system requirements, and later we would like to understand how the security requirements gonna impact our project. So as you can see, now we are going back to the requirements after we designed the model and everything. Then we will perform some automated testing, okay, against those system, against the security requirements. First, we will start by with opening the projects. Just a quick note about the projects and the integration with source control are very important for complex projects like this one. So I already create a project for this demo, and you can also create a project from scratch by going to the home tab, then new, and then projects. And later, once you create the projects, you open it, you would like to integrate with source control or versioning systems like Git. So I already integrated with Git, and this column is for Git. Okay. The reason why I'm doing that, because this project is quite like big, large, and I would like to manage my files and other artifacts in a different and better way. Then we're gonna define the requirements. Okay, as I said, we're gonna start with the system requirements. And so with requirement toolbox, you can edit your requirements directly within MATLAB and Simulink by using an app, an interactive app, which is called requirement editor. Okay, this will allow you to edit requirements within MATLAB and Simulink environments. Say that you are using another requirement management tool and you would like to integrate with MATLAB and Simulink requirements capabilities. So there is a workflow for that to import requirements from third-party applications like Microsoft, Excel, OpenDoor, and so on and so forth. So these are the system level requirements. Okay, maximize this a bit. So they are basically related to communication, imaging, and then power source, sizing, and so on and so forth. We have a couple of them. Some of them are related to the platform. Some of them are related to the flight control. Okay. With these requirements list in mind, we would like to build an architecture for our quadcopter. So this is the architecture. You can build such architecture using System Composer, and it has functionality for that. For example, you can use components from this library, from the component library. You can include views and stereotypes, profiles, and so on and so forth. And then you apply this, and you perform some analysis at the architectural level. Then the next step for us is to model the design itself. So we have four main components of this system: the ground station, the threads, then the quadcopter plans alongside with the controller, and of course we have a visualization component just to show the scenario. Let me go now to the vehicle and show you the platform for our quadcopter. It's actually modeled using a guidance model, and you have the choice. So if you want to go with a higher fidelity or a lower fidelity, so MATLAB and Simulink add-ons for modeling UAVs offer you plenty of options for that. We are using this guidance model for this example. The flight controller is implemented here, so you can decompose the components into smaller components and integrate your controller. So we have a guidance compute block or subsystem, and then for the controller is just a PID, okay? And we're doing some calculation after so that we get the control signal. The output of this will be visualized, and the output is the state of our UAV platform. All right, so next we would like to link those requirements. So the requirements can be linked to different components. Let me go to requirement manager. This requirement can be, can be visualized and then linked to different components. Okay. Where are they saved? So they are saved in a separate file, system requirements. Okay. I'll open that file and show you. So it's actually the same as I showed you before. So next is to implement the behavior. We spoke about that already. And we have two scenarios. With a normal operation using a Mavlink protocol, we get this performance. And then with another scenario where it's needed to build a custom protocol, a Mavlink protocol. This Mavlink is heavily used in, drones design for communicating between the ground station and the UAV. But it's simple and easy to spoof. So this scenario is just to verify how good are the performance of our design against those three. To do that, we are simulating. We simulate the model using this sim, and then we also assess the risk using this matrix. As you can see with this basic Mavlink protocol, we have a high risk of being spoofed, and so what we would like to do now is to introduce some requirements so we test against them and we validate our design. So speaking about this, the security requirements are saved in this file, okay? And I can show you that. It's one requirements related to GSC or to the ground station to the UAV communication. And we would like to verify our design against that. But before that, we know that our Mavlink isn't working properly and we would like to customize or build a custom one. So we build a custom one and then we simulate again the risk. So in this case, it's moved to the yellow area. It means that there is a risk, but it's not as critical as before. The last thing in the workflow is the automated requirement-based testing. So you can build test cases using test manager. So you can build a test case and then you specify the model under test. You specify the parameters for your iteration. You also can define the iterations and everything. And later you can run your test and see how that gonna work. For us, we would like to check if our custom Mavlink gonna work properly or not. So we have created 3 iterations. One for the communication without spoofing, others for other iteration with the spoofing, but one with the classic Mavlink and another one with the custom communication link. So we have in this case 3 iterations. I can probably show you the test I ran before. And as you can see, with the custom protocol, our test has passed successfully. And we conclude this live demo, okay? And we are open to questions. So let me go back now to the presentation. So this is the workflow, and I have added everything here. We're gonna share the slides, and you can go through this at your pace. I have added all the steps or the phases and the relevant part. Just one more word about the implementation part. We didn't cover it properly. It's just one small part, which is the Mavlink communication, but MATLAB and Simulink offer more than that. So you can connect your MATLAB and Simulink environment to a drone, flying taxi, or whatever you are building, and then perform the hardware in the loop testing, or what we call, if you want to be specific, PX4 in the loop or autopilot in the loop. It depends on the autopilot that you are using. A summary of our demo. So we mapped model-based design to a quadcopter system design and verification. And I would like now to mention about upcoming workshops where we're going to cover more hardware implementation and system and testing.